Why did I say it is non-orientable? So remember, I defined a surface to be non-orientable if it contains a Mobius strip, if a Mobius strip embeds in there. So why is it called non-orientable? So then, and the reason is, well, if you watch that video of V Hart with Mr. Wind and Mr. Ugg, you might have seen what this phenomenon. So what happens is, so suppose you are walking on the Mobius strip, okay, and suppose let me sort of so this is you from top, okay, so this is the top of your head, and this is your left hand, and this is your right hand, okay, and you're facing this way, okay, and you're kind of that's why that's your left and that's your right, and you're kind of walking this way. Okay, so what happens when you when you walk, and when you kind of cross over, you come back, right? But this time what happens is, so remember this this side is so this side here is identified with that side with a flip. So what happens when you come back is that so what you called your left hand is now here, and your right hand is now there. Okay, so if you think about it, so when you're left hand, when you're right here, right, so the left hand is kind of sticking out, right? So but since this side is identified with that with a flip, so when it sticks out, then it kind of comes here, right? And so that's your that's where the left hand kind of arrives. So when you walk around a Mobius strip and come back, I mean, somehow your left and right hands are interchanged, right? So this is what you sort of see in this video of V Hart as well. And so this is what is known as non-orientability. Okay, so there's no well-defined notion of left and right on this surface. This doesn't happen on a sphere or a cylinder or something which is orientable. Okay, so this is what is known as orientability. Okay, and so the enemy of orientability of surfaces is this presence of a Mobius strip. If there is some Mobius strip in the picture somewhere, then you are sort of not orientable. Okay, because this kind of thing will happen if you walk around the Mobius strip. Your sort of notions of left and right will get interchanged. Okay, so this is what why this is called non-orientable. Okay, yeah. So now coming back to this other question which we had was this. We had a hexagon, and we identified opposite sides. Okay, and the question was, what surface do you get? Okay, so right. So now this is harder to imagine. Instead of a square, opposite sides identified, you see that you get a torus, but this time you have these extra edges. It's sort of harder to visualize, but what one can use is this classification of surfaces, right? So one thing that you can try to guess is, okay, so what is its Euler characteristic? You can try to you can actually compute it, right? And you can also see whether it's orientable. So here it's not orientable because there's no flip in any of these identifications, right? So if we had if this edge was identified, if the top edge was identified, the bottom edge with the flip, then we would have had an embedded Mobius strip here, right? So this would have been an embedded Mobius strip, but we don't have that, right? So we have the arrows going in this way and this way, and so each of these identifications that we are doing, identifying edges, there's no flip. Okay, so there's no Mobius strip in the picture, so there's no embedded. So notice that there's no embedded Mobius strip. So therefore it's orientable. So it's an orientable surface. Okay. The second thing that you kind of try to do now that you kind of know what the thing is, what is the Euler number? Okay, so what is the Euler number? So we can do the same thing like we did before. We can, in this hexagon, we take all the edges, Okay, that's my graph, and all the vertices of these things are sort of vertices of the graph. Okay, this graph is certainly connected, and its complement is this one face with the inside of this hexagon, right? The only thing is that we need to, sort of count how many vertices and edges are there after identification. Okay, so now we have to sort of see, you have to track these identifications and see which ones are getting identified. So first of all, we see that there are 3 edges, right? So because this edge and this edge is identified, that's, let's say, the edge number 1. This edge and this edge are identified, so that's 2. And this edge and this edge are identified. So there are 3 edges. So number of edges is 3. How about the number of vertices? Okay, so here you have to keep track of the identifications more carefully. Remember that when you identify opposite edges, you also identify the corresponding endpoints, the vertices that lie on the endpoints, right? So this guy, let me draw this as a circle, this in blue. When you identify it by a translation this way, well, so in the opposite edge, then this guy gets identified with this, right? But this guy's, so this is when I'm thinking of it as the sort of the end point of this edge 3, okay, the edge 3 with an arrow, it's got ends at that blue vertex, okay, and then I look at the opposite 3, so that's the same edge, right? So it has to have the same end point. So these end points are identified. But this circled blue vertex is also the beginning, the starting point of 1 on top, the top edge, right? And so that also gets identified with the starting point of this bottom edge, because the whole identification of the top edge and bottom edge includes these endpoints, right? So these circled guys are all identified. And similarly, you can check that if you, if I circle these guys yellow, so this gets identified with this, again, because it's both the starting point of vertex 3, and then this gets identified, the same vertex gets identified with the top vertex, okay? So when you follow, how when you glue, certain vertices get identified, and when you keep track of that, you'll see that there are 2 vertices after the gluings, okay? So there are, so the number of vertices is actually 2. Okay, so after these identifications, all right. So and the number of faces or regions is 1, because there's only 1 inside. So you see here that this the Euler characteristic or Euler number is 0. Okay, so you see that we get a surface. By the way, so whenever you glue sides of a polygon, we get a surface because so I'll give a definition of a surface in a little while, because around you, if you're an ant, you will always see a small disk, which is just like you're on a sphere or on any other, sort of on a flat plane, right? So you'll see a disk around, because so if this edge and this side gets identified, if you're an ant sitting on an edge on your right, or let's say you're facing sort of the right of this screen here, so then on one side of you, you will see this half disk. On the other side of you, you will see this half disk, and these 2 half disks glued together to give you a full disk. So that's the definition of a surface. You're locally around you, you think that you are on the plane. Okay, so so this is a definition of a surface. I'll come to the formal definition in a little bit, but so you are a surface, you are orientable, and your Euler number is 0. Can someone? So now you can look up the classification, right? You know that up to topological equivalence, there is only one such surface. Okay, the surface is determined by its orientability and its Euler number. So if you are Euler number 0 and you're orientable, and you are a surface which is closed, right? There's no boundary edge in this whole discussion. All edges are used in this for gluing. So then you must be, the classification of surfaces implies, so 1 and 2 implies via the classification of surfaces. So you have this surface must be a torus. Okay, the torus is the surface which is Euler number 0. It's orientable, and yeah, and it's a closed surface, right? So this is this is the solution of this other question which I had. What surface do you get when you identify? And if you try to picture what happens to this graph, okay, so this graph that I drew, so then you can do that. So what happens is that your graph in this glued up torus looks something like this. So there are two vertices. Remember, there are, sort of after doing, let me do this. So this was the circled vertex, and this was the other yellow vertex. There are two vertices, and there are three edges in this graph, right? So there's the one edge, there's a second edge, and there's a third edge that goes behind into the hole and out, right? So this is, and then the complement of that, so that's harder to see in this picture. The complement of this graph is this hexagonal region, which is a valid region. It's a flat region on the plane without any holes. It's something that can be bounded by a planar graph. Okay, so this is what you get. Okay, you get a torus, right? So all right. So, and then there was another question about what is a closed oriented or orientable surface with Euler number equal to -2. Okay, so this is so this is somewhat more tricky, perhaps, if you're sort of new to Euler numbers and you're trying to sort of build things, the constructions we've seen. But you can maybe reach that if you sort of notice a few things. Okay, so some of you already noticed that if you have some surface, okay, so let's say, so you have abstractly some surface. Okay, so maybe you build it up by sort of gluing so taking a polygon and gluing edges. If you make a hole, if you sort of cut out a disk, okay, so this is your sort of, you take a scissor and you just cut out a disk, and you kind of make a sort of a hole in your surface. Okay, this is surface minus a disk. Okay, so then what happens to the Euler number? So the Euler number, now you get a surface with an edge. Okay, so there's a boundary edge. Sorry, I shouldn't say an edge. I should say a boundary, right? So so maybe it's confusing if I say boundary and edge altogether. So it's a boundary. So you get a surface with boundary, because once you cut out the disk, there's what remains is a circle, which is boundary edge now. So if you started off with some surface, maybe it has boundary, maybe it doesn't. It doesn't matter. But if you cut out a disk, you get another boundary. Okay, and now what happens to Euler characteristic is that it decreases by 1. Okay, so this is something that, because what you could have chosen, remember the Euler characteristic doesn't depend on what graph you choose, right? So you could have chosen a graph which has a vertex. Let's say it has a vertex on this disk you're about to cut, and it has an edge like this, right? And it bounds a region, right? It bounds a region which counts as 1 in this, when you do this alternating sum. Now, after you cut it, there is still that vertex and there's still that edge here, but there's no region, right? So you're not adding 1 in that when you compute this Euler number. So your Euler characteristic would have decreased by 1. So this is something that, so let me just note. So this is called an excision. If you excise a disk, the Euler number, or remove a disk, let me say remove or excise a disk, the Euler number decreases by 1. Okay, so this is something that might be useful. Okay, so to build surfaces for a given Euler number. The second thing that you can notice, you want a closed surface. So now you know that the closed surface has no boundary edge, right? So I don't want these boundary edges to be still there in the picture. So how do you remove boundary edges? So, well, if you take two surfaces which have one boundary edge each, and you glue the boundary edges, you sew along these boundary edges, then you get something without boundary, because you've sewn. On one side you had a boundary, and the other side you had a boundary, but you just sort of sew these along this boundary. So then you would not get so there's some questions also. So let me sort of keep the chat in front of me also. Right. So there's these boundary. So it gets sort of, when you glue boundary edges, your boundary disappears. We've seen that with a Mobius strip. Remember when we glued two Mobius strips along the boundary, then we get a Klein bottle. Klein bottle is a closed surface. It has no boundary edge. Okay. So the second thing to sort of observe is that if you glue along boundary edges, glue two surfaces. So let's say two surfaces along boundary edges, then the glued surface doesn't have boundary, right? So let's assume that both these surfaces have one boundary edge, and when we glue them, then that so then there's no other edge now, right? So so it doesn't have a boundary. Okay, so it's something like this. So you have one this is one surface, this is another surface, but when you glue, after gluing, so then if you're an ant, you don't see any edge, right? So you see a nice disk around you. Okay, so there's no trouble. Okay, this surface doesn't have any. So so what happens is if you observe these two things, then you might be able to guess what this surface would look like. Well, what you can do is, if you take a torus, okay, and so that has Euler number 0, and you cut out a disk. So remove a disk. Let me say remove or excise a disk. Then what you get is something, it's a torus, but now it has a hole, right? So that has Euler characteristic, Euler number -1. Now it's a surface with boundary. And now if you take two of these guys, okay, and then you glue up, okay, so then what happens is, right, so you can check. So now you glue these. So now you will get some surface without any boundary, okay, and this, what happens to the Euler characteristic when you do this gluing along a boundary edge, okay, so this, maybe I should have mentioned it as part of the second observation, is that the Euler characteristics add up, okay, so maybe let me also sort of mention, so also the Euler numbers add up. When the glued surface would have the Euler number that is the sum of the two Euler numbers that you had. Okay, so this is something that, again, you can convince yourself by trying to imagine that there's a graph with a vertex and an edge around the boundary circle, vertex and edge boundary circle. When you glue them, the two vertices get identified and the two edges get identified. Okay, and then the rest of the vertices and edges, have a count, just like they had before, and so you can actually sort of check that the Euler number adds up, right? Is the sum of let's say chi1 and chi2, where the chi1 and chi2 are the Euler characteristics of these surfaces. So this surface has like number chi1, this is surface chi2. When you glue them like this along these boundary edges, then you can check, this is an exercise, that the Euler numbers add up. So in this case, the chi1 is -1 and this chi2 is also -1. And when you add up, you get a closed surface, which is -2. Okay, and you might worry about whether it's orientable or not. And it turns out that since I started with the torus, which has no Mobius strip on it, you remove a disk, it will still not have a Mobius. You glue it as shown here. You don't have to introduce any flips or things like that. Then you actually get an orientable surface. Okay, this is something slightly more tricky, but but you can check that this is an orientable surface. So the sort of the answer to this this question of what is a closed orientable surface with Euler characteristic -2 is this guy. Okay, this is a surface of genus 2. Okay, so this number, it's a torus with 2 holes, right? I mean, so you might have come across this in descriptions of topology. So surface with 2 holes is called a genus 2 surface, and you can have, so in the list of closed orientable surfaces, you start off with a sphere which has genus 0, Euler characteristic is 2, and genus is equal to 0. Then you have a torus, which is Euler characteristic is 0, and genus is 1. It's 1 hole. Then you have a genus 2 surface, which Euler characteristic is -2, genus is 2. So genus is, Euler characteristic is always 2 minus 2g. Okay, that's the formula. So chi is 2 minus 2g. It decreases by 2 each time. Okay, and each time you add a hole, and there's this Euler characteristic -4, genus 3, and so on. Okay, so you add, each time you add some kind of hole, and this is, turns out the classification of surfaces, the theorem that I mentioned earlier, is that these are all the closed and orientable surfaces. Okay, any closed and orientable surface, it has to be one of these in the list. Okay, so yeah, so this is so let me just say it's called a genus 2 surface. Okay, and this is one of my favorite surfaces.